So what if actually this presentation is done remotely? What if what you see on the screen now is a hologram? What if actually I'm part of this conference using AR, VR, stuff like that? Is this science fiction? Okay, so my name is Michael Holmberg. I do come from Extreme Networks, and what I'm actually going to talk about is the the transport network architecture as well as requirements for 5G. So kind of the intro I gave you is, you know, that's going to be reality at a given time once you start to get into 5G. So I'm going to spend like the next 25, 30 minutes talking about the requirements for 5G. I guess a lot of you guys heard about 5G. A lot of you guys heard about, you know, the kind of challenge it's going to put, because you are going to start to talk about, you know, self-driven cars. You're going to start to talk about different new applications, which obviously at the end of the day is going to put some requirements on the network itself. So with that said, let's actually start this journey with taking a, you know, step back. So basically looking at the, you know, metro networks a couple of years back, what was the key thing? You basically had, you know, more dynamics at the access and obviously less dynamics in the core network. Now, from a you know, feature function point of view, obviously this used to be like layer 0 to layer 3. And you started to look at things like SDN, you know, flow-based. You started to look at applications more and more cloud-based. So that was like back then. So if we actually move ahead, so I'm going to spend like 2 minutes on a video for you guys. This is just to build a foundation for what I'm going to talk about. I guess for a lot of you, this is not really new stuff. I think this is just a good kind of recap of 5G. Can we get the video rolling? I can actually get with the clicker. Sorry for that. A short technical break, I guess. Yeah, it's embedded. Yeah, yeah. It's embedded. Okay. Okay, so sorry for that, guys. So instead of the video, let me kind of walk you through the same thing. The intent of the video was just to show you, you know, in a nutshell, 5G. But I guess, you know, doing it with slides is basically the same thing. So as I said, if we kind of look at 4G, what we have today, you look at, you know, latency requirements like 10 milliseconds, which is kind of huge, right? If you start to look at 5G latency requirements, you talk about sub 1 millisecond, microseconds. Why is this? This is due to the new applications. What are the applications? As you know, autonomous cars, self-driving cars, you know, remote surgery, things like that. So it's truly putting new demands on the network itself, because at the end of the day, you still have a network in place somewhere, right, for the transport. And another thing is bandwidth. So think of this, if I'm actually able to get like 10 gig on a handheld compared to what you have today, I can get like 4K video on my handheld. So, you know, to build up the story more and more, obviously this is going to put a lot of requirements on your network infrastructure. So, a few use cases here. Obviously, looking at mission-critical networks, that's one use case. Today, you have the Tetra networks, you have the P25 networks, you know, mission-critical networks. 5G is thought of actually being the new technology for those networks as well, with things like push-to-talk, with things like sensors, kind of understanding if I'm about to crash, to, you know, get emergency people on site, all that stuff. You have a high definition video, you have a bunch of new applications. And then looking at the next one, IoT. We all love IoT, right? And IoT is massive. I mean, if you start to look at IoT today, you have your fridge is connected to fridge is connected, your coffee maker is connected, your sensors connected, basically everything. So here's the thing. So some surveys actually say that by 2024, you are going to have like 15 billion IoT devices, 15 billion, which of 4 billion is going to be mobile connected. By the same year, 2024, you're going to have 1.6 billion 5G subscribers. Now, why am I going through all of this stuff? Due to the fact that at the end of the day, you still have a network in place. Right, so if you look at the two other ones, you had mobile broadband. Now, let me throw out a question here. If I have 10 gig on my handheld, the speed, if you now look at, the fixed broadband, how many of you have 10 gig home? Not that many, I guess. If I can actually have, mobile 10 gig broadband, that's a complete new interesting application as well. So I think you kind of get the picture here what I'm talking about. So, as said, you see 10 times increase in the bandwidth from 4G to 5G, and I talk about the bandwidth on the physical device, my handheld. You see, new kind of use cases come into play. Not only the consumers anymore. You go into logistics, you go into transport, you go into healthcare, you go into, as said, a bunch of new applications. I'm not going to read out the complete slide, but I just want to build out a picture here that you understand that, a lot of new things are coming along with 5G. And then you go into the MNOs, the mobile network operators, you do business to consumer, you do business to business, you have different models, so to speak. So, 5G, ignore kind of the wireless or the radio parts. What I want to focus on is on the two left-hand side squares, which is basically network slicing together with low latency networks. Now, going back again saying that low latency, if I have a self-driving car, I need to have truly low latency, right? Which means I need to support it in some way in my core network as well, in my fixed network, because that's where I'm going to end up basically pushing everything. And here's a key thing with 5G. 5G is cloud native, which means that all of the services are moved into the cloud. And guess what? I need to have a network in place to get to the cloud. So, as said, it's cloud native. Now, latency being one thing. The other thing is that, as I kind of, had as an example public safety networks, or, remote surgery, or autonomous cars, I can't really have those applications competing with me as a consumer looking at 4K video, looking at, some stuff on the net, which means that I actually go into something called network slicing. Now, what is network slicing? So it's basically a way of providing communication for different applications based on the 5G architecture you have. So looking at the topology, how flexible it is. So as a recap, as I said, the RAN, the radio access network, used to be like hardware-based everything, right? Now with 5G, as said, this is cloud native, which means that I have a minority of the physical functions out at my radio access part, on my radio towers. The rest of the services, the intelligence is actually in the cloud. Everything is virtualized. To add to that one, NFV, SDN, once again, it's virtualized, right? You have your network function virtualization with, things like virtualized firewalls, load balancers, all of that stuff resides somewhere in the cloud. Then you go into kind of starting to look at the cloud. Now I have something called the MEC, which is the Mobile Edge Cloud, or the Multi-Access Edge Cloud, which basically means that I'm starting to throw more stuff out to the edge, to the access from an intelligence point of view. Now, on the previous slide, you saw kind of TCP optimization as well, which kind of raises a question that is IP truly, the protocol to use? So there are some thoughts of going into something called ICN, which is more like information-centric networking, which basically goes hand in hand with the MEC, the Mobile Edge Cloud, that you start to put more intelligence, more stuff out to the cloud. You spread it through the cloud. But at the end of the day, you still have a network in place here. So another thing here on 5G, you split the control and the user plane, which is basically you have a separate data plane and a separate control plane. So that's kind of building the picture. And still, as said, you have a core network in place. You still have a packet network somewhere to actually get me from the RAN, get me from the virtualized or the radio environment all the way into my virtual services within the cloud somewhere. So to kind of walk you through network slicing in 2 minutes on a high level, think of this as you have your orchestration layer, you have your RAN orchestration, basically your radio access network orchestration. You have your transport network orchestration, and you have your core network orchestration. So basically orchestration of everything, right? Then you get into your network slicing part being the services. Now you might actually have a given enterprise customer who is using one network slice for his services, enterprise services. Then on top of that one, you have another network slice, which is basically for my RAN network. As I said, if you go into a C-RAN, being a cloud RAN, you have a different network slice for that one. What I'm trying to make a point on here is that you can't compete on the bandwidth on basically what you have in a normal core infrastructure today for different applications. You need to have some intelligence in place. Now, well, somebody could ask, define network slicing. What is it? It could be a VLAN, it could be a VXLAN tunnel, it could be some kind of a virtual connection, physical connection, you name it. It's not really defined yet. The point being is that you need to be able to separate between different traffic classes, because some of the traffic might have requirement for ultra-low latency, stuff like that. So, as I said, you then have multiple slices, basically for different functions. You might have your 2G, 3G, 4G transport, that's a slice. You might have your Wi-Fi offload. You might have different network slices for different functions or services within the 5G architecture. So basically, this obviously puts some requirements as I kind of walk you through, saying that I need to be able to make sure that if I have a given low latency application, I need to orchestrate that in the right way with policies, with different things on the service layer here. Okay, so 5G transport is more than just a necessary cost. It's truly an architecture, right? But it's an architecture that is focusing on the future. We don't even have a clue of all the applications we are going to see here, right? It's going to be a bunch of new applications coming out with this one. And this is part of the universal edge. As said, you have SDN in the picture, you have your packet optical network, you have still a transport network in place here. So let's spend a few minutes on this one. So this shows you now, I'm kind of drilling into the architecture itself from a network point of view. What this shows you is the 4G compared to the 5G. Now, if you look at the details, on the 4G, you basically have your radio head, you have your base unit, and then you go back to your mobile, basically, services. What you see is you have a backhaul and a fronthaul service. This is a matter of networking, right? And you can see the latencies that's basically given for the 4G. Now, if you compare to the 5G, as said, you start to virtualize things, which means that you have a radio unit, you have an RU, you have a DU, which is a digital unit, and then you go into a CU. Define a CU. CU is actually an Ethernet switch. And then you go into your core, which is your packet core, which is your backbone, basically. So with that said, as you can see, and as I was mentioning, the latency requirements are pretty heavy here. Not only that one, but the interesting thing, if you look at the synchronization, for 4G, it's GPS. For 5G, we talk about TSN, or basically PTP, and SYNC-key. Now, this raises a question due to the fact that I need to transport synchronization. I need to transport it through my network. And as I mentioned, everything is cloud-based. I need to make sure that I get from end to end with a sync. So TSN, what is it? It's part of the 82.1q family. It's defined as provide deterministic messaging on standard Ethernet networks. So to put that into some context, I'll skip over this one. To put that into some context, this is a recap of basically the needs you have from a network point of view. What you see is here the same broken out to the different part, the front haul, the mid haul, and the back haul. And as said, you see the technologies you use here, front haul TSN, which is the sync part, could be WDM, active or passive, dedicated fiber. For the mid haul, you go into OTN, WDM, you go into low latency Ethernet. Keep in mind, low latency Ethernet. And then the backhaul is kind of the carrier Ethernet that you have today. So another thing is, everything is model driven. So you actually start to go into automation, massive scale automation. And kind of taking a step back here, I didn't talk anything about the radio part, but what you basically are going to start to see is, picocells, microcells, small cells. You're going to see, a huge proliferation of antennas, of basic base stations, because you need to have 100% coverage. You need to provide, as we've been discussing, the 5G requirements here, which basically means that I need to be able to configure all that stuff in some way. Hence, you go into young models, data models together with netconf. And they basically have something called the SON, which is kind of a way of self-organizing networks, which basically is an automation providing automated tasks to configure all this on the RAN side. This is just a model of that one. What I truly like on this slide is if you look at the red square, saying that with the full mesh packet network architecture, cross-domain control will allow operators to support end-to-end services. Cross-domain, which means that we do not talk anymore only of a network. We talk cross-domain, network, applications, services, everything. So, taking a step back, I talked about PTP and SYNC-key. Now, here's a challenge. SYNC-key is a hardware-based sync, which means that if I'm going to provide SYNC-key synchronization, I need to have each and every device understanding SYNC-key. It's hardware-based. Now, as we all realize, that's not optimal, because you're not going to have an end-to-end network providing hardware sync. Hence, you go into PTP or precision time protocol defined by 1588 v2, which is the same thing packet-based, which means that you're basically going to put a timestamp within your packet in some way, which basically means that you have a clock architecture, or hierarchy actually, where you would have a master clock and slave clocks. All of the slave clocks would actually adjust to the master clock, and basically saying that you need to have a capability within Ethernet to actually timestamp a packet. going from Ethernet's nature being, connectionless into basically timestamping something, which means that I need to understand and timestamp my traffic to get synchronization done. And this kind of goes back again to my use cases I defined with truly, mission-critical applications, with new applications we are going to see, which do have a huge demand for things like that. I'm not going to go through this slide. This kind of just shows you PTP, what it does. It's basically a way of how you start with send your time, you basically acknowledge your time, and eventually I know what is the skew on the time, and I'm going to correct my PTP field in my Ethernet header to basically be able to cope with that time. So, with that said, obviously I do come from extreme networks, so I need to kind of build a picture here for you guys that the stuff I talked about, the synchronization, we do have products supporting that. And obviously, fact being is that if you looked at the 5G architecture I was showing, the DU is the Ethernet switch. You need to provide synchronization on those ones. We have different platforms supporting functions like that. Now, what I actually want to throw into the picture is the automation. And as I said, it's well defined for 5G, the cross-domain automation. Guess what? We actually see the same thing happening in enterprise network, in data center networks, and so on and so forth. So what the basically picture shows you is automation in steps. Nobody wants to go from CLI to cross-domain automation with all the workflows, all that stuff. So what happens is that you start small. You might start to automate your network infrastructure, talking about, say a close fabric. You automate that close fabric. Next step is that you bring into the picture some more automation tools like Puppet, Chef, Ansible. You provide APIs with RESTful APIs, so on and so forth. And then eventually you go into cross-domain orchestration, which we tend to think being, truly the thing due to the fact that you get into a scenario where you have not only the network anymore, but you have basically applications as well as webhooks to be able to do something based on an event. What we use is Stackstorm as the engine. It's something called the Extreme Workflow Composer. But basically to kind of build a picture for you in 1 minute, what you'll have is think of a network where I actually have something triggering an event, an SNMP trap. Based on that SNMP trap, what I want to do is try to remediate my network, try to re-enable that port, for instance. I also want to have webhooks into applications, one being a Slack channel for my NOC. The other one might be a webhook into an application, being Splunk or being anything, I might want to open a trouble ticket in my trouble ticket system. So this is kind of the automation, the cross-domain automation as such. And as said, this kind of falls from the 5G all the way into the enterprise and the data centers. And we do have some automation suites for fabrics, for tenant provisioning, so on and so forth. So with that said, I have 1 minute to go, and that's basically showing you the 5G architecture on a high level. Now, my key message of these 30 minutes is keep in mind that you still have your core network, you still have your network in place. Obviously, your demands for that given network has changed and will change with 5G. Not only from the synchronization part, but also from a bandwidth-hungry application point of view. Okay, thank you.